We're now on page 3 of the Chapter 8 practice test. This is the fun stuff. This is my favorite part of the chapter, is writing the sums and difference. Remember, this is called expanding and condensing. So write as a sum or difference just means take one log and write it as many logs using your properties. So shall we write the properties up here at the top so you have them all here all together? So the first property we learned was called the product rule. So in exponents, when we multiply exponentials, we keep the base and add their exponents. Well, logs, same thing, same base, but we add the logs. So the log of a product, multiplication, turns into the sum of logs, just like we add exponents in multiplication. Then the next property we learned was the quotient rule. And when we divide exponentials, we keep the base the same and we subtract the exponents. So log is the same way. A log of a quotient means subtract the logs. And then last we had the power rule, which says take the power and put it down in front. Whoops. So that'd be 2 times log of x. So those are the properties we use for expanding and for condensing. So if you have them up there, then you can keep looking at them. So hopefully you notice this is a product rule. So we need to turn this into a sum of logs. So it'd be log base 4 of 64 plus log base 4 x to the 5th. So I'm hoping that you notice there's a couple things left to do here. Remember how I said look for logs that don't have any x's or y's in them? Lots of times they can be simplified. So this is what I should be saying in my head. Can I rewrite 64 with this base? Because remember, if the bases are the same, they undo each other. The answer is the exponent. And the answer to that is yes. 64 is 4 to the 3rd. So that's why I told you to memorize those cubes, because they keep coming back. 4 to the 3rd, 64. So we can rewrite that as log base 4, 4 to the 3rd. You see the inverse property there, so those are going to undo each other. The answer is just going to be the exponent. And in the second part, do you see what needs to be done with the second term? Power rule, just like up here. So this would be plus 5 times log base 4 of x. And we know this one can't be simplified because it has an exponent in it. So my answer is going to be 3 plus 5 log base 4 of x. That is my answer, because these undo each other, so the answer is the exponent, and then this one we had to do the power rule. Fun, huh? I love these. This is my favorite. Okay, so next we have the quotient rule, and remember how we learned you have to take care of those? So that we could rewrite as x to the 1/3. And the reason why is because we need to apply the power rule. So when you see a radical, change it to a power. So it's the power over the index. That's how we got 1/3. So since this is a quotient, it's going to follow the second rule where we subtract the logs. So it's going to be log base 3 x to the 1/3 minus log base 3 of 81. So hopefully again you recognize that there are things to be done here. On this first one, does everybody agree this is a power rule? So 1/3 times log base 3 of x. And on this one I go Oh, Miss Norris told us if there isn't an x, it probably can be simplified. So if this is 3, can I write 81 using 3? So do 3 to the third. No, that's not 81. 3 to the fourth. There it is. So I can. So anytime there isn't an x, look and see if you can rewrite it so that you can do this inverse property that we did here. And we can. So that would be log base 3, and 81 is the same thing as 3 to the fourth. So do you all agree that's just going to be 4 for that second term? Because the base of the log and the base of the exponent are the same. Therefore, the answer is just going to be the exponent. This one I can see can't be simplified further because there's an x. So we're just going to write 1/3 log base 3 of x minus 4. Because those two undo each other. The base of the log's 3, the base of the exponent's 3, so the answer's just the exponent. Inverse property of logarithms. Okay, so those are called expanding, or this book uses a little bit different language. Right as a sum or difference. So we took 1 log and wrote it as 2 logs. Sometimes it's 3 or 4. And then on this next set, we're going to be doing exactly the opposite. We're going backwards to a single log. So we're going from this step to that, or this step back to that. So that's what right is a single logarithm. So we still use the same rules, but instead of going this way, now we're going to be going this way with the rules. See how this is a single log, each of these? So this first one is addition. So I know it's going to be a multiplication problem, but I also know that I have to do the power rule first because I'm doing the opposite. Here my power rule was last, but now that I'm doing the opposite, I do my power rule first. So let's first rewrite this as log x to the 6th. So these powers have to go back, plus log y squared. So now we're at this step, which says take 2 logs. Wait a second, my paper clip's coming out. Take 2 logs that are added, and they go backwards into a single log of multiplication. So take 2 logs that are added, and they go backwards into a single log of multiplication. So this would be log of x to the 6th, whoops, y to the 2nd. That's a 6, sorry about that. Sometimes my brain moves faster than my hand, and I was already writing y's exponent. Okay, so addition goes backwards into multiplication. And here I can see we have subtraction and we have addition. So what I like to do is if there's one subtraction, I like to put it at the end. So when I go to rewrite during this first step, I'm going to put it at the end just because we know it's going to go down to the denominator. So I just like listing it last. So we're going to have natural log of 7. And then we're going to have plus natural log of y squared. And then we're going to have minus natural log of x cubed. So this stays the same. I just switch these around because this one's going to go in the denominator. Remember, anything that has a negative sign in front of it, the argument goes in the denominator. So I just put it at the end. And then this is going to be in the numerator. So these two are going to get multiplied in the numerator because it's addition, and then this one's going down to the denominator. So we can already go to our final answer. Natural log, write your division. The positives stay in the numerator and get multiplied. And the negative log, its argument goes down to the denominator. So writing as a single logarithm is easier than the other ones, doesn't take very much work, but your head does have to be able to go backwards with the rules. So they're pretty easy. I like those. Okay, next we have our 8.7b stuff where we learned how to solve exponentials. Do you remember how sometimes we could make the bases the same and do the one-to-one exponent rule? Sometimes we had to take the log of both sides, but we always have to have the exponential isolated before we can start. Isolated so we can start, isolated so we can start. Oops, not isolated, because this is the exponential part right here. So it needs to be alone before you can take the log of both sides. And that's probably the most missed one of this section because students don't do that first. Okay, so we have 9 and 27. So does that ring any bells there? Can they be written with the same base? Yes, they can. 9 is 3 to the second. 27 is 3 to the third. So if you recognize that, you can save yourself some trouble and you don't have to use logs. So 9 is 3 to the second, and then outside I have x minus 2, and 27 is 3 to the third. So this does get distributed, so it'd be 3 to the 2x minus 4 equals 3 to the third. You guys all remember the one-to-one log property says, and exponential property says, if the bases are the same, in exponentials you equate your arguments. In log, okay, I said that backwards. In exponentials you equate your exponents. In logs you equate your arguments. So 3 is already equal to 3, so we don't have to worry about it. So then you just set your two exponents equal, and that's how you find the value of x. So if the bases are the same, equate your exponents. So then we add 4, 2x equals 7. So that means x is 7 halves. And you could write 3.5 or 3.5, but no reason to. Usually we just keep it improper. So give an exact solution, give an approximate. This one is exact, so that means it doesn't have an approximation. So that's all we're going to do there. Okay, on the next two, though, you should notice that we cannot make the bases the same. So when you can't make the bases the same, then you have to take the log of both sides. And we learned in 8.7b that if it doesn't have an e, you can just do regular log. If it does have an e, then you should do the natural log. So this one doesn't, so let's just do regular log. So log 5 to the x equals log 1.4. So are you wondering why we did this one this way and we're doing this one this way, or does everybody know? Here we could make the bases the same. That's why we did this method. 5 and 1.4, we can't make the bases the same, so that's why we do the log of both sides. So remember what I said? Tell yourself, well, this is solved. That means I'm trying to get x alone, but how can I get x alone when it's up in the air? So that's your hint to do the power rule. So x times log of 5 equals log of 1.4. Then to get x alone, you divide both sides by log of 5. So my exact answer for this one is log of 1.4 divided by log of 5. My approximate answer will be log of 1.4 close divided by log of 5 close And it says 2 decimal